Hello and welcome to this lecture on life cycle assessment for ENST 481. So life cycle assessment is a tool for the systematic evaluation of the environmental aspects of a product of service through all stages of its life. It basically provides a decision making, it's a decision making instrument that's based on environmental impacts. So it takes into account multiple impacts of a product on the environment. And there actually is international standards for this. So ISO 14040 has the framework and principles, guidelines, and the life cycle initiative, which basically talks you through how to do a life cycle assessment and how to conduct the inventory and the guidelines for doing each assessment and interpretation. So, what a life cycle assessment is it's basically you can think of it of five processes from cradle to grave. So, first is going to be the collecting of the raw materials that are used, taking that material and processing it into building whatever it is that you have, processing it so that you can manufacture your product. So, building it, using that product, and then finally disposing of that product. So you have raw materials, processing, manufacturing, use, and disposal. And basically, at each one of those stages, you are going to quantify the impacts on human health, ecosystems, and resources. And so again, often other assessments will only be when you use this product. You use a solar cell, how much energy comes in, how much energy comes out. What's the impact of using a solar cell versus the impact of using greenhouse gas or coal production for electricity production? It's just the use. But here we're actually going to go through all the materials we need to actually build that cell, to mine the silicon, for example, processing it into the raw material that we need, making the cells, distributing those cells to where they're going to be used, using the cells, and then disposing of the solar cells. So it's a complete analysis that takes into account from cradle to grave, not just using the solar cells, for example. So again, the output is going to depend on the goals and scope of the study. So what you will do is do a functional boundary of the system, and you'll say, for my LCA, this is what's inside my boundary, and this is what's outside my boundary. And so you have to have a scope and goal of your study. And based on the goal of your study, you're going to have a functional unit, and everything is going to go back to that functional unit. For example, kilograms of meat produced or kilowatts of electricity. Whatever it is, everything is going to be normalized to that functional unit. Then you're going to have the methodology impact assignment, where basically you're going to assign impacts to each stage. And again, it shouldn't only be focused on energy and greenhouse gases. It really should be the whole swathe of all environmental impacts, eutrophication, ecotoxicity. The applications of the results can be used for product development and improvement to reduce waste or redundancy, for strategic planning. So, for example, Walmart has made an environmental footprint, which is based on LCA. Where basically you can become a preferred buyer. So if my Walmart environmental footprint, which again is a version of an LCA, shows that my Mamma Mia meatballs have a lower impact than other competitors, then I can be a preferred seller and I actually get a cent or two more for each of my products because I rank higher in their environmental footprint. And so it can be used in businesses to try to increase their sustainability by increasing the sustainability of the products that come into that business. It can be used for public policy compliance. So, for example, if you get a biofuel grant from the government or even Department of Energy grant, many of these grants require LCA so that they're making sure we're not kind of shifting from one impact to another. So we have to do an LCA of the research that we're doing. You can use it in marketing. So again, in waste management or, producer responsibilities, we're going to make sure that our products actually can be disposed of well, or that the products coming in, the materials that we use are sustainable. And again, LEED certification for building certification. Again, we have many LEED, silver, and gold certified buildings on campus. And one of the ways to get points through your LEED certification process is actually to do an LCA. So it's not required in LEED certification, but again, if you have a gold or platinum building, you want to get as many points as possible. So you're likely going to do a life cycle assessment of your building, and then you're going to improve on your building based on those life cycle assessment results. And then if you do that process and document it, then you can get extra points to lead you from kind of LEED certified to bronze, silver, gold, and platinum. So why use it? Again, it's a quantitative analysis, helps to prioritize in the decision-making process, allows you to make comparisons between, other products doing it one way or another, or with a standard. Again, it's useful for creating those standards. If we want to get to here, this is what we need to think about. Helps reinforce feedback. So if you change a process, you can show that that process is actually helping to close some loops, and you're able to kind of do that circular economy, that eco design, where the waste products go into the end product of something else, become an input. Again, it's comprehensive, where the impact is connected to the function. So again, we decide on what the functional unit is, and that impact is based on that functional unit that you define. Avoids problem shifting. So if we're doing something where, yes, we're reducing greenhouse gases, but we're increasing eutrophication, that's going to come out in the LCA analysis. Again, there's a distinction because it's science-based info, everything's quantified versus a value choice. And so again, there's a distinction there. There really isn't value choices in the LCA. It's more of a quantitative approach. And again, there's a standardization. So there is ICO standards that you have to follow when you're doing an LCA. So again, the first thing you do is the goal and scope definition. So what is it you're trying to do the life cycle assessment of? Then you're going to do the inventory analysis. So for example, for our solar cell, for example, we're going to look at all the raw materials, the silicon, the doping agents, the steel, everything that went into that. And then we're going to do the impact of all of that and getting it to the factory. So the manufacturing of those materials, the transportation of those materials, the processing of those materials to get them to the factory, and then the processing that we use within the factory, how much electricity we use, how much fuel we use, everything that we do within our factory, for example. And then once they get distributed to the user, what is the impact of that during the use phase? And then finally, the disposal phase. So that's all part of the inventory analysis, so that we know each of those life stages. We have to quantify all of the emissions and inputs. And then you put it in so that you get your impact assessments on all of the categories that you do. Then you're going to interpret it, and it's going to go back and forth. We're going to do a sensitivity analysis. We're going to make sure we have everything right. Does this make sense? And then finally apply it, so you can make more informed decisions about your process. So again, our first thing is our goal and scope definition, where we're going to do our functional unit, our system boundaries, and what's the criteria for the data that we'll use. The inventory, we're going to draw a process diagram. We're going to mine for information and process all that information that we need to create that inventory so that we can do the impact assessment. And the impact assessment, we're classifying everything, we're characterizing everything, we're normalizing it back to our functional unit, and then we're evaluating the process. And then finally, we're going to improve that process by doing a sensitivity analysis and reporting. So these are from examples of some midpoints and endpoints to get your impact score. So for example, you would have carcinogens, non-carcinogens, ozone layer depletion, radiation, which would all lead into your human health. We have mineral extraction, non-renewable energy leads into resources. Eutrophication, ecotoxicity that would lead into environmental quality, global warming standards that would lead into climate change. But then even in those points, you have these impact factors. There's a lot of impact factors you can use. The ones that are often used are global warming potential, acidification potential, eutrophication, human toxicity, ecotoxicity, resource consumption, heavy metals, and stratospheric ozone. So those are often the ones that are used. There's other ones that you can use. Again, depends on which tool that you use. So what happens is we have to get all of these into those impact categories. And so what we'll do is we'll take sulfur dioxide, NOx, and HCl emissions, And basically we use an equivalent. So those all go to one unit, which is an SO2. So SO2, sulfur dioxide, is going to go directly, but these are actually going to be converted to a sulfur dioxide equivalent. So then everything's in sulfur dioxide units so that we can actually create that acidification potential based on sulfur dioxide. The same thing for eutrophication. We actually take the different nitrogen and phosphorus, and we actually do a conversion from phosphorus to nitrogen based on eutrophication potential. And then that way everything's in a nitrogen unit or an equivalency. And then we do that for eutrophication. Again, for global warming, again, that methane has a different impact factor than CO2, about 28 times. And then again, CF6s are about 23,000 times. And so again, for each unit of those, we're going to convert those into a CO2 equivalently so that we can get a global warming potential. So again, all of this is based on our functional unit that we use. So again, it's used for all comparisons. It depends on the goal and the scope of the study, and it's usually defined on the end product that you're going to use. So for example, if we have a functional unit here, might be based on the environmental impact, based on if we're having cattle grazing, so it might be based on the kilograms of meat produced. So everything would go back to kilograms of meat produced. So again, the steps of this inventory process: we're going to prepare for data collection, collect our data, validate our data, relate the data back to the processing unit, relating it back to the functional unit, aggregate it again so that it all goes to those equivalency, and then make sure that our system boundaries are correct. So we have to go back and change the system boundaries if we just can't get data. And so we might have to put something outside of our system boundary if we don't have equivalent data to go in. There's a lot of different tools to use. In our group, we often use SemiPro. And again, in those categories, so for example, if I put in steel, it'll actually have a lot of the inputs. So I have to pay for SemiPro, and it'll have a lot of the inputs actually in there. And so it'll tell me, for steel, what's the acidification potential and what is the eutrophication potential and everything based on how many kilograms of steel I'm using, for example. And so a lot of these things have already been categorized. EPA has its own, it's called a WARM, it's a waste production model. But again, it often just looks at greenhouse gas emissions. Carnegie Mellon actually has one that's an economic input-output life cycle. So it not only does the LCA, but it adds an economic component that's not in the international standards. There's also the environmental benefits. So GREET has the National Renewable Energy Lab from the US has created a greenhouse gas emissions model called GREET. There's an eco-LCA that actually takes into account ecology a little bit more specifically. Gabby and Umberto are actually softwares like SemiPro that do LCAs, and with different, again, the background, how much you pay for the background material and how detailed it is just differs a little bit between these different softwares and how many impact categories they have. So there's two different approaches you can use. So there's attributional approach versus consequential approach. So attributional is going to be, how is this product produced? What's the current situation? Historic tracking of mass and flow. So you're just saying, here's our system, here's what's coming in, here's what's going out, and this is the impact. Versus consequential is going to be the consequent of buying this product or choosing A over B or adding a new component. So consequential, you can think of as kind of more of a comparative approach, while attribution is just going to be taking a single system from cradle to grave. Consequence is going to be kind of choosing one or the other, comparing one against the other. And so here's an example of a consequential. So we can look at a life cycle of getting a paper bag versus a life cycle of getting a low density polyethylene bag, a plastic bag. And so what this allows us to do is look at these impacts of these two bags. And so we can see here that that based on different categories, eutrophication, based on acidification, greenhouse gas emissions, metals, smog, we can see where the impact between these two products are similar. So for example, the metal content is similar, but the acidification potential and the smog factors are different, with more for the plastic bag. Again, here's another way of doing it. If we look at taking everything as 100%, how much less do we have with one bag compared to the other? So for carcinogens, for example, it's actually a lot higher with the with the paper bag, and we actually only have 10% of that with the low density polyethylene. But if you look at the other categories, acidification, ozone, potential greenhouse gas emissions, again, the life cycle of the paper bag only have 70% of the greenhouse gas emissions that a low density polyethylene bag would have. So again, it allows you to compare in multiple categories what the effects are of using two different products. So I'm going to take us through an example that we've done in our lab. So this is a fluidized bed combustion of poultry litter at the farm scale. And so what we did was we looked at the operational changes. So we had poultry litter that was being put into a fluidized bed combustion system. So what they're doing is they're taking the poultry litter from the poultry house. They're actually combusting that poultry litter. So that organic matter, instead of combusting like coal or natural gas, you're combusting the organic matter of the poultry litter and then using that for heat production. And that heat is either going directly into the poultry houses through a radiant heating system to heat the poultry houses instead of using propane to heat the houses. And, or it's also going into an engine, a Rankine cycle engine, to produce electricity. So again, the fluidized bed combustion system produces heat and it can produce electricity. So this is a waste to energy process. So the life cycle assessment sensitivity analysis saw that if we use it for heating, it was less sustainable than actually using natural gas or for heating propane in 12 of the 18 impact categories. So we did 18 impact categories, and of those, 12 of them were actually less sustainable with the heating because it wasn't being operated in the right manner. So then we looked at if we change the amount of electricity, because the problem was a lot of the electricity we were using a lot of electricity to run the pumps, to run the conveyor system, to operate this system instead of producing electricity because the Rankine cycle engine that they had only worked only was working, a small percentage of the time. So if we just added 10 more percent electricity production than what they had from this process. And so we allowed the electricity production to run the system instead of using outside electricity to run the system. Then we found the highest change in all the impact categories. And basically what happened was that we can see here that when we increased the electricity production, we actually increased the sustainability. It was more sustainable because we weren't using electricity off the grid to run the system. Instead, we were putting electricity on the grid. So here's the design. So here we have the poultry houses and the litter. This is what poultry litter looks like. It's poultry manure coming out of the litter, out of the poultry houses. But again, we had this ramp that we have to run with electricity to come in here. And then we started with electricity, this heating process. And then again, that heating process is the combustion chamber. And then the hot water is produced that's used to heat the houses. And then the idea was they would use the electric generator, but it wasn't being used in this system as long as it could have been, as much as it should have been. So again, here's the inputs to the system. So here's our system boundary. So we didn't actually use, we just had the poultry litter come. So we didn't actually take into account the growing of the chickens themselves. Our input was the poultry litter coming out. And the output then was the ash that was coming out, the fertilizer used and transporting so that we could use the fertilizer. And then everything in the process was the startup diesel you needed for the combustion system, the backup boiler, the boiler itself, the emissions from the combustion system, the generator that we had, and the electricity production. So the functional unit was actually 1 megajoules of energy. And so everything was calculated based on 16 months of monitoring of this fluidized bed combustion system, including the mass of energy in and the mass in, the mass out, the energy in, energy out. And so this is kind of what this would look like. So basically we looked at all of these different inputs. So each of these boxes are different inputs. And based on how much raw materials we had to build the combustion system, the poultry litter coming in, the mass coming in, how much energy was coming out, heat coming out. And then we compare that to, we had one of these for the gasification system. We had one of these assuming there's no gasification system, where we're using natural gas to heat the houses, or we're using propane to heat the houses. And so again, this is kind of in the SimiPro software system. So you have the amount that you have, the unit. And so for example, for so much poultry litter, you can figure out what is the carbon dioxide emissions, the nitrous emissions, the sulfur dioxide for each one of these things that you put in. And again, it'll provide embedded data in the software, but if you have your own data that you've actually measured, then you can put that data in to modify your data set based on what's in the software. And so you can see here, we have kind of a baseline scenario where they had so much small electricity production coming off the system, mainly using it for heat, an improved scenario where we actually used it for heat and electricity. And then again, we can look at the construction materials, the air emissions, the storage, and then how much the amount, the units, the kilograms per megajoule. And so this is where we got it. Some of it we got from our own monitoring, and some of it was based on the lifetime of the system, or based on how much poultry litter we had, or literature data as well. And so if we look at the LCA outputs, so again, this is looking at the relative inputs. So for each of these systems, so for the poultry litter combustion, for example, you can see the electricity use was the one that had the biggest effect of in almost all of the categories. So that was the electricity, not the production, but the electricity use that we were using to actually run the system, the pumps and whatnot for the system. And so the actual fluidized bed unit itself, again, had some metal depletion because it was a lot of steel. And so that had a large impact. And again, we had the combustion emissions here. You can see that impact here. And so again, we can look at each part of the process and see where our largest emissions are. So we could clearly see that the electricity use on the system was too much, and we need to reduce the amount of electricity that we were using and increase the amount of electricity that we were producing from the system. And so again, when we look at the combustion of poultry litter versus the combustion of liquid propane natural gas, or liquid propane gas or natural gas. And so again, you can see these three things. So again, ionizing radiation was much more with the fossil fuels compared to the poultry litter. But again, we had more eutrophication from the poultry litter. So again, you can kind of, and we had more metal depletion from the poultry litter because we had to build this big combustion system. So it allows you to kind of figure out where your impacts might be. So we did our sensitivity analysis in our report results. And basically, when we look at the percent change, what we found is that if we change the amount of electricity use, we actually saw that all of our categories went more sustainable. And so I'll go through one more quick example. This is one not for renewable energy, but it just kind of shows you the importance of your inputs and outputs. So this was where we actually took food waste and manure composting. And so we had, again, the food waste production was outside of our box, and inside our system boundaries was transporting that food waste to our composting unit, the composting process and the turner that we had to use, the distribution and the use of that compost, and all the emissions to soil and the avoided emissions. And so what we found was the most important factor was actually the methane emission factor during composting. Again, during composting, you shouldn't get a lot of methane because it should be an aerobic process. But again, what we found was the literature showed that it was all over the place in terms of what kind of methane emissions that you had. And so what that meant was when we did the minimum amount of methane emissions, we saw that, again, that the combustion electricity had the largest component. But when we were doing the maximum amount of methane emissions, we could see that, again, these decomposition emissions had a much higher potential if we were getting methane emissions based on literature values of how much methane emissions they see during composting. So again, we kind of did a minimum, an average, and a maximum. So it really depends on what values you're putting in your LCA. The other thing that we found is during the process, whether there's electricity, the turning, the tractor loading and mixing and stacking activities had the largest impact. But again, we found that when we looked at what we were avoiding, when we avoided the use of peat moss, because peat moss usually comes from Canada, and that's what this system was currently using as a soil conditioner. And when we used the compost instead of the peat moss, we actually had much lower reductions because the peat moss comes from northern Canada and from Canada and the northern US and had to be trucked all the way down here. And so again, when we think of the compost phase, the food waste composting system had net positive gains in all impact categories. We used a Tracy 1 methodology instead of SemiPro. But again, the composting processing stage had the largest impact, with decomposition emissions contributing the most to global warming, acidification, and eutrophication under the average and maximum. But again, not when we had the minimum or no real methane coming out. But again, it highlights the importance of minimizing the impacts associated with methane, N2O, and ammonia emissions during the composting process. So if you can really control those emissions, then yes, it's a sustainable process. But because it's an open system, if you're not controlling those emissions, you can actually be contributing more impact to the system with food waste composting. So again, these are just some process you can do so you can hone in on what really are the biggest impacts that you need to focus on during your operational system. So those are just some examples of how it can be used. What we will talk more about is the use in biofuels, because we're getting ready to go into our biofuel section, and we're going to talk specifically about net energy ratio and fossil fuel ratio and life cycle assessments of biofuels, and how those assessments have been used to kind of improve the process and different policy decisions on what biofuels we use, based in the US and in other countries, based on their kind of total impact. So that's life cycle assessment.